and nuclear power specifically, along with hydropower and solar power. I run the energyeducation.ca website, the largest, most comprehensive, and most used energy education resource online for adults. Check us out. But you're here to listen to these fine people talk about, so I'll start all the way to your left with Steve Oldham, who serves as Carbon Engineering's CEO. Carbon engineering has a particularly warm place in my heart. It was started at the University of Calgary by a colleague of mine, also a physicist, David Keith. And they have some of the most exciting technology about carbon capture, sequestration, and related issues, which I'm hoping we'll be hearing about in this panel. You've done a lot of interesting things, including various roles in robotics, aerospace, various technology, and we're here today to talk about carbon engineering and how carbon engineering is going to actually do some amazingly hopeful things for us in the future with climate change, which is, of course, something that Terrestrial Energy, our host, is very much involved with. Dr. Shannon Briggs-Sitton, was that close enough?
It's close.
And I even asked first. Bragg-Sitton?
Yes.
There we go.
Thank you.
I was so worried about the Sitton that I was focused on that. So the manager of the Integration Department for Nuclear Systems and Design Analysis Division at Idaho National Labs. So the very important challenge of having renewables on our grid is going to involve having a lot of other things on our grid as well. So as a nuclear engineer by trade and training, she is well positioned at Idaho National Labs to talk about energy from a systems perspective, which I think is one of the things we'll be discussing today. Energy from a systems perspective as it pertains to how we can actually transition our entire energy system. So one of the big things that we're going to be focusing on is that nuclear, not just for electricity anymore. And I believe you've got a fair amount of expertise, and you lead a team of
Yes.
world-renowned experts at Idaho National Lab, and we'll be talking about that today. Finally, coming all the way over here to Simon Irish, who is the CEO and director of Terrestrial Energy, one of the most exciting small modular reactor, molten salt reactor technology companies. I'm particularly excited about it because it's, to my mind, Canadian, although I understand that you're actually living stateside in the 11th province. You have 20 years of global investment banking and investment management experience in both New York and London. But I'm most excited to hear about your current work here with Terrestrial Energy and how you see Terrestrial Energy as one of the leaders in going forward to the next generation of nuclear solutions for climate change, and not just, as we said, in electricity, but advanced fuels and so forth. So I'm looking forward to this discussion. In the same order that I just introduced you, would you please give at most 5 minutes? I'm hoping and I'll be gurring you about the time. So can you give us each 5 minutes? And you're comfortable starting?
Sure, if that's what you wish. So good morning. Still morning. Yes. Good morning, everyone. Let me start with scaring you a little bit. So climate change is scary. We have so much focus on stopping emissions, and that's really, really hard. But let me be even more scary. According to all of the climate scientists, if we stop emissions tomorrow completely, we still have a climate change problem, because 95% of the CO2 that is causing the problem with climate change is already up there. So we can stop emissions, but it's not enough. So the good news, our company started work 9 years ago on developing technology that would extract CO2 directly out of the atmosphere. The bad news, there's only about 100 people on the entire planet working on this. Even worse news, I'm one of them, so the other 99 had better be really good. So we have a working pilot plant here in Squamish, British Columbia, just up the road, and we've been pulling CO2 out of the atmosphere since 2015. We just announced last week a 500 kiloton per year CO2 capture plant in Houston, in Texas, with our partners Occidental. So why is this of relevance to this discussion? One of the opportunities when you capture CO2 from the atmosphere is you can turn it into a synthetic fuel. if you have hydrogen and energy. Why is synthetic fuel important? So synthetic fuel offers a way to decarbonize any vehicle. In our plant in British Columbia, we've been making synthetic fuel since 2015. I have some, oops, and we broke it right here. So this is the CO2 inside this fuel is yesterday's CO2. It was emitted by one of you maybe when you took a plane journey or a car, or maybe all the way back with a cow breaking wind in 1750 or something, but here is the CO2. So when you put this fuel in any vehicle, it's 100% compatible with every car you see out there, every plane you see out there, every truck you see out there. When you put this fuel inside that vehicle, the vehicle's carbon neutral. When the fuel is carbon neutral, the vehicle is carbon neutral. So electric cars, fantastic. $30,000 for an electric car, 1 billion cars in the world, that's $30 trillion to address the emissions of cars, which contribute 13% of emissions to 5% of the problem, because 95% of the CO2 is already up there. So what do we need to make lots of this? We need energy. And that's why what terrestrial energy do, and what other companies, Net Power, the nuclear sector, renewables sector do, is really important for us, because we use renewable energy and the CO2 we capture from the atmosphere to make this fuel. And hopefully that's brief enough.
It was.
And I'm happy to take any questions.
All right, we will
Right time.
hold off questions,
Yes,
and I have some myself, but if you can please
Absolutely.
carry us forward.
So I work at Idaho National Laboratory, and some of you may be familiar with the national laboratory system in the US, and to others it might be very new. INL is just one of 17 national laboratories in the United States that are operated by the Department of Energy. INL is unique in that we are the only nuclear energy laboratory. There are others that work in the nuclear sector, but we are operated by the Office of Nuclear Energy, and we also do work in renewable energies, biofuels, many different things, but that is one of our primary focus areas. And we have a long history in developing and demonstrating nuclear technologies. And the Idaho site is about 900 square miles, so we have a lot of land, and we have demonstrated more than 50 different reactor types, either for research and development or for potential future commercial applications in the Idaho site facilities. And currently we have 4 reactors that are operating at Idaho. One was recently brought back online, which we find very exciting after it had been sitting dormant for a while. And we have plans to build many new reactors, both for research and development, as well as demonstration and prototype and commercial units on the INL site in the coming years. So I'm a nuclear engineer, as Jason mentioned, and I have interest in making sure that when we have a reactor, we've invested all of this capital into building that facility. We want to make sure that we use it to its greatest extent possible, meaning that right now we use our reactors for electricity alone, for the most part. What we'd like to do is better utilize that energy available, that energy density, that high quality heat from those reactors, not only to produce clean electricity, but also to bring clean heat into industry, to bring new fuels into our transportation sector, whether that be hydrogen directly or synthetic fuels that are much cleaner overall. So we do research in this area at INL. And the program that I lead on integrated energy systems was officially established, I would say, about 5 years ago via collaboration with our renewable energy laboratory in Colorado. Now, why that's important is because we are looking in this direction to move beyond just electricity, not just because of the desire to have more and more clean energy, but also because of the impact that variable renewables are having on our baseload energy systems. As more and more renewables come online, this is great because it is working toward reduced emissions in our electric sector. But some of you may have listened to some of the other nuclear sessions here at the SEM meeting, and it's really disturbing to find out that as more and more renewables come online, our emissions aren't going down because the variability of renewables causes some economic challenges to baseload plants. And what we're finding is that it's pushing some of those nuclear plants out of the market. And in the US, at least, some of those plants are shutting down early. So instead of reducing power, which reduces economic benefits of that plant, we want to redirect that energy. So let's accommodate solar and wind in this grid that we have, but at the same time, use that excess energy from nuclear plants to produce things such as hydrogen, clean hydrogen, that could be combined with CO2 from the atmosphere and make synthetic fuels, or can be used in the industrial sector for steel manufacturing or producing fertilizers for our agricultural industries. So at INL, we've invested in a number of different areas to build modeling and simulation systems to help us design optimal configurations where we look at how we optimally size the different systems that come together. What size should my hydrogen plant and my synfuels plant be when I couple it to a 300 megawatt or a 600 megawatt reactor? And then we look at how that should optimally be dispatched so that we have that best economic performance that we can possibly have. And we also have experimental systems where we're building up a non-nuclear electrically heated laboratory where we've put in a hydrogen production system, high temperature steam electrolysis to produce hydrogen. Collaborators with me are also working on other methods for hydrogen production that are also being considered around the world. So I encourage you, if you're ever at INL and in that area, come see our laboratory where we're trying to demonstrate how we'll control these systems, how we'll connect them, looking at nominal as well as off-nominal operation before we implement those on a nuclear system. So I'm encouraged by the group here. I'm glad to bring nuclear to these clean energy discussions, and I welcome your questions. Thank you.
Thank you. Thanks. So I think there's a sort of logical flow to these introductions. Steve has indicated that synthetic fuels require two ingredients. They require carbon and they require hydrogen, both of which are not in short supply. You can get hydrogen from water, and you can get carbon from carbon dioxide. The ingredient that is in short supply to make this work economically, and it must work economically, price must drive deployment of synthetic fuels, price must drive deployment of clean energy systems. The element that's in very short supply is cost-competitive clean energy in great scale. And it's that missing piece that we're seeking to provide. That missing piece can be provided very effectively with nuclear power. Nuclear energy is unique. Nuclear energy, the energy from the atom, of which there are two types, is far, far more scalable than fossil fuels. We think about fossil fuels as a unrenewable energy resource that if you include coal, probably will last at probably current rates, maybe for several centuries. Nuclear fuel is infinite. Nuclear has more energy muscle and more clean energy muscle than anything else we know. So nuclear energy is an excellent provider of that missing piece, that clean energy piece that can make this entire supply chain work, the supply chain of synthetic fuels. We're looking to provide that energy with a technology our technology is called the integral molten salt reactor. That uses a molten salt, a generic molten salt technology. We have packaged that technology, which has been demonstrated before at Oak Ridge National Lab. We've packaged that technology in an innovative design. And what we're seeking to do with this technology, and I can talk about this technology in great detail, but what we're seeking to do with this technology is to provide a cost-competitive alternative to fossil fuels as the principal energy source in an industrial economy. And that's so what's exciting about our technology is it is commercially transformative. We believe our technology can deliver a clean energy substitute to fossil fuels, and that makes it capable of providing the missing piece in the synthetic fuel supply chain. In terms of where we are at the moment, we've been engaged with the Canadian regulator for 3 years. We've got 2 years to go. In 2 years' time, beginning of 2021, if we're successful with that review, we will have a commercially very important designation. Our system will be designated as a reactor system that has no fundamental barriers to licensing. At that point, we're in a position to start commercial discussions with users of that technology, which will be the existing nuclear fleet. So the first system we expect to come online at the back end of next decade, so 10 years time, and that system will, at that point in time, be commercially demonstrating that our technology is capable of delivering that essential missing piece that makes synthetic fuels, carbon neutral synthetic fuels, a commercial reality. They too must be cost competitive against alternatives. They can be cost competitive against alternatives if the primary ingredient of the process is also cost competitive, and that can be our integral molten salt reactor power plant. Thank you.
Thank you. What I'd like to do now is I'd like to actually ask questions of the panelists in the same order they just presented, and I'd like to give the panelists an opportunity to ask the other panelists a question. Because I've often noticed that panelists are like, hey, wait a minute. And then we will see how we are doing for time after that. I suspect this could become a bit of a free-for-all. But to go back over to our carbon engineering, first just a yes or no question. The hydrogen that you usually use for fuels, that would come from water, correct?
Correct.
Okay.
Sorry, yes.
Correct was acceptable. So you mentioned the ability to create fuels for the current fleet. This is particularly exciting because a lot of people aren't aware of the fact that even if we were to wave a magic wand and make all of the vehicles being sold right now electric vehicles, it would still take close to 15 years to completely phase out the fleet that exists. So it sounds like your company is able to actually provide fuels for the cars and trucks and planes and boats and so forth. So you are actually able to make kerosene, Jet A, diesel, gasoline, the entire suite?
Yeah, fundamentally we make hydrocarbon, and that hydrocarbon mix can be focused on kerosene, gasoline or diesel, but it's chemically identical with no blending limitations. Unlike, for example, ethanol, you have maximum 5% ethanol at the pump. We don't have that characteristic. So we can be used 100% or we can be blended to whatever extent the blender wants. But fundamentally what we produce is 100% compatible with any existing vehicle without modification.
So then presumably in addition to being compatible with the vehicle, it would also be compatible with the current infrastructure.
Yes.
So your gas station, your petrol stations
Yes.
can all use the same thing.
Yes.
What is the energy requirement for me to put a liter of gasoline into my car?
Yeah, it varies according to the implementation. Our process needs both power, because we start with big fans, and it also needs heat, because part of our process is heating up calcium carbonate pellets that we produce to extract the CO2. So depending on the configuration of the plant, we have whole electric plants, we have combinations of natural gas plants. The plant that we just announced last week in Texas will be predominantly natural gas, because natural gas is abundant there. And for anybody who asks, of course we collect any emissions in our process. Our facility is carbon neutral itself. So it varies. Overall, the energy efficiency of production all the way through to fuel works out as about 42%. So energy in versus energy out. The way we interact with the energy industry is we go to new sources of energy. So we don't want to pull power off the grid that can be used for other things. What we do is we go to the renewable energy industry and say, wherever you want to build a plant, but you don't today. For example, if you're a solar provider and you're out in the middle of, you have a site in the middle of the desert, but there's no demand there, or the transmission grid isn't built out there.
Sure.
So we build a facility with them there, put our facility right next door. CO2 is available in the air everywhere, and that way we get the cheapest cost of renewable energy, and it's additive renewable energy that wasn't previously on the grid, converted into liquid fuel, which, as you know, is a great way to transport energy, and the transportation costs of liquid fuel are very cheap.
So just to run some numbers, a liter of gasoline has 35 megajoules of energy in it, and at 42% efficiency, you're talking about needing roughly 90 megajoules of raw energy. Now, when you say 90 megajoules of energy in, are you talking electricity, or are you talking all of the energy you're putting in with heat and with electricity?
So so I'm not the technical expert here, so let me answer
Sorry,
the
you have a
question
physicist as a
slightly.
moderator.
I should have seen that come up. So let me try and answer the question that I know and look at it. So, and this is related to the legislation that exists in the market today for carbon neutrality in fuel. So when you look at a fossil fuel is 100 grams of CO2 per megajoule. Our fuel will be less than 10. So it'll be 10 times less carbon intense
That's for a life cycle.
Yeah.
Okay.
As a fuel than traditional fossil fuels. Biofuels typically are in the region 40 to 60 grams per megajoule. So again, because we use recycled CO2, not emission delayed CO2, like a flue stack, if you use flue stack CO2 and make a fuel, when the vehicle runs, all you've done is delay that original emission. We eliminate from the atmosphere and then put it back, net zero.
Okay.
So that's the way that I look at the energy and the carbon content.
So I want to get to your question real quick, but can your nuclear fleet provide the types of energy that he's talking about?
Well, we have a Generation 4 reactor system that provides two forms of heat, two forms of energy. One is power, and presumably there's power required for your process and heat as well.
Yeah.
I don't know at this point, Steve, the heat requirements of the process that you're building at Carbon Engineering, but it has the potential of supplying those two important.
And we can go all electricity, by the way. You know,
Okay.
I talked about natural gas as a sensible choice for us in many locations, but we have a plant variant that is 100% renewable electricity.
Yeah. Okay.
So, Idaho National Labs is a lovely facility. I've been there twice with students. Would love to go back again, potentially without students. It's more fun. Well, I love my students. There's a funny story that's not appropriate in front of the camera. But Idaho National Labs has done amazing work on this portfolio for decades, including the fact that reactors at Idaho National Lab first powered Arco, Idaho, the first city to ever be entirely powered by nuclear power. Kind of a surprising thing that I wish Idaho could brag about more. It's some great nuclear engineering, nuclear science, and nuclear technology. Would it be possible with the Idaho National Lab structure to create some of these add-ons, to do demonstration not just of the nuclear technology, but to actually have a working plant where you have say a molten salt reactor or one of the other small modular reactors on site, but then not just produce electricity, but, sorry, you're nodding, I'll just let you talk.
So we're working in that direction right now in a few different avenues. So I mentioned that we have a high temperature steam electrolysis system that we've installed in our laboratory, and that laboratory includes a number of the components that would be a part of this integrated system already installed. Now we're starting small. It's a 25 kilowatt electric system, but it's also coupled to a chemical synthesis reactor that we can, based on the input feedstock to that chemical synthesis process, we can produce upwards of about 50% of the industrial process chemicals that are out there. So including synthetic fuels, we can actually emulate within our laboratory. We have plans to go to a larger scale system, a 250 kilowatt electric hydrogen electrolysis system. And then right now we're also planning for research and development associated with the first NuScale plant. For those of you not familiar with that, NuScale is another one of these small modular reactor developers. It is an integral pressurized water reactor, and the first plant will be built on the INL site. Well, the unique opportunity with that is that it's a 12 module unit, and one of those modules I get to play with. It will be a fully commercial plant, yet that module will have a research and development component to it. And part of that, one of the highest priority, is integrated energy systems, meaning it will have a modified secondary side to include thermal energy storage and to include coupled energy users. Now, hydrogen is one of those that's at the top of our list. But we plan to do this in a way that we can first demonstrate hydrogen using high temperature electrolysis, and then after a couple of years of testing, move to something else. And bringing in a synthetic fuels plant as well is certainly in the realm of possibility. And we've also been in discussions with a number of other reactor developers, advanced reactor developers, to also demonstrate those concepts either in a commercial type of unit, or commercial prototype, or a demonstration plant on the INL site. As I said, we've got a lot of land out there and we'd like to use it. We'd like to demonstrate these systems, not just the energy generation side, but the energy use side as well.
In addition to a lot of land, they also have some amazing researchers that I've had the opportunity to meet some of, not nearly as many as you have clearly, but some exciting work going on at INL. from the hydrogen perspective, I'm assuming you're sort of hydrogen neutral. I mean, hydrogen has a lot of uses. It can go directly into a fuel cell. I know there's some exciting fuel cell work being done at INL. But it can also be used in this synthetic fuel process. Anything to say on that front?
Well, as I mentioned, we have this chemical, the synthesis reactor, which allows us to demonstrate how we can use that hydrogen in a number of different pathways. We also can use that as an upgrading to biofuels, and in our neighboring high bay, we have a biofuels plant as well, a process demonstration unit. So we can demonstrate that also. We are working with some companies right now to look at use of hydrogen in a direct reduction of iron process for steel manufacturing, which can bring some of that steel manufacturing back into the US that's not there now. And we see these types of plants being built in Europe as well, where a premium is being paid for clean hydrogen. So hydrogen right now is primarily made by steam methane reforming, meaning we take that natural gas that, yes, is very abundant in the US right now and extremely cheap, and that's broken down using the heat from combusting the natural gas to break down that process. If we could just replace that heat component with clean heat from a molten salt reactor, high temperature gas reactor, or even a light water reactor, we can reduce emissions in that process of steam methane reforming, or we can go to these other processes for hydrogen production, being water electrolysis, either low temperature electricity driven, high temperature that also includes a thermal component, or hybrid sulfur processes. There's a number of avenues where we can get clean hydrogen into industry. Fertilizer production as well is another application, into clean fuels, into the transportation system. So we're working on a number of those avenues at INL and in collaboration with the other laboratories in the US as well.
Thank you. I'm going to ask my questions of you and then open up to the panel to ask cross-panel questions. So please be thinking of that while I'm grilling him. Trying to change gears entirely now. One of the big statements that keeps being made about the fact that we're emitting a lot of CO2, 35 to 37 gigatons of CO2 per year, is that we have always been allowed to do that for free. So a lot of talk is now going into various carbon pricing strategies, whether this is carbon taxes, carbon levies, cap and trade systems. A lot of the solutions that people in solar and wind and so forth talk about needing are those market signals that come from policy. Does your deployment for synthetic fuels, does your business model require these policy implemented carbon pushing, or can you make it happen without those?
Well, that's a good point. Our business model is not contingent on a carbon price.
Excellent.
It's based on our system being able to compete against fossil fuels in competitive energy markets.
Okay.
Yep.
Sorry, I was expecting a...
Can I comment on that? So ours is, fundamentally, if society doesn't see that there is a cost of carbon, there is no value in removing it. And as such, our process will cost more than fossil fuel. Of course it will. So just as organic chicken sells very well because some people prefer to have a well brought up chicken, so I expect that there will be a recognition in society that a better product is one with a lower carbon. So I just wanted to give the counter, Simon. Sorry to...
Do you have anything to reply to that?
I think there's an interesting opportunity here, and Steve, this is a thought I had this morning when we were preparing for the panel, is that carbon is probably the best method of storing hydrogen, and the problem that one has about contemplating a hydrogen economy is that hydrogen is a really terrible thing to store. If you do try and store it and use a vast amount, it's worse than liquefied natural gas. You use a vast amount of energy to actually store it. It's just generally a poor energy currency. But gasoline, on the other hand, is an excellent energy currency, and strangely enough, because it's such a good energy currency, we pay more for 1 unit of energy from gasoline than anything else. I think it's between $20 and $25 an MMBTU. So if you, the thought I had in terms of of implementing these strategies in the absence of a carbon tax, you could nonetheless have policy support in the form of a mandate to have gasoline being 10% synthetic fuel, and that would require whether synthetic fuel, whether the CO2 from synthetic fuel comes through your process, and that would turn CO2 into an asset.
Yeah. Oh,
The people, the people who have CO2 would recognise it as an asset, because those delivering synthetic mandated to deliver a blended fuel have to source.
so that's what the Californian low carbon fuel
Yes.
standard does, and I think it's tremendously effective. So if you're a fuel supplier in California, you have to move from 100% carbon intensity fossil fuel down to 80%, 80 grams per megajoule by 2030. So California has basically set this linear scale dropping like this. So if you're the large provider of fossil fuel into California, which remember is the 5th largest market in the world, then you have to find a low carbon alternative to blend. You can buy carbon credits, but there's a limited amount. So, right now one of our largest investors is Chevron, and why did they put money into carbon engineering? Exactly what you just said.
Mm-hmm.
Did you have anything you want to add to this?
So just building off what Simon said, we've done a number of analyses looking at different reactor types. I'll say one thing, I'm a big fan of advanced reactors, and I think we need to get there, and the higher temperatures they offer is fantastic. But if we can't keep our current fleet reactors operating, we're not going to get there, or at least not in the near term. And so we also look at how we can utilize light water reactors in these applications as well. And so our analyses have shown the cost to produce steam from a light water reactor or from some of these advanced reactors that are on the forefront of development, we're competitive right now to steam from natural gas. But we need to work through some of the technical challenges and the regulatory challenges of getting that steam to the fence line and getting that steam to these processes that need the heat or need the steam directly. But if we look at the raw numbers, we're competitive right now. We just need to do it.
Can I ask a question of the panel? For the rules? Is that okay?
I had another question
Okay, go
for
ahead.
Simon, but I think it's actually more fruitful if you ask your question.
Okay, so I'm going to ask a different type of question because I'm not a nuclear physicist or that type of thing. So to me, one of the biggest challenges in what we collectively are doing is public perception. And just to frame this point, so when I joined Carbon Engineering about slightly less than 18 months ago, the company had less than 3 months of money worth left in the bank before we went bankrupt. So the first thing I did as CEO was hire a PR company because I felt that our story is a good story and we wanted to get it out there. By doing so, we raised $90 million from a whole bunch of different companies. And astonishingly, 20 million people on Facebook watched an interview with me, which is just insane. My point in saying all of this is the public needs to hear hope on climate change. They hear doom and gloom all the time. So I work very hard in my part of the job to drive that. So I'm interested in your sides of the business. You clearly have an awful lot of technical initiative in what you're doing, and you can talk to multiple technical crowds. But have you guys looked at how do you engage with the general public and say, guys, there's hope here, and this is what we need to do?
Well, if you look at polling analysis, I think it elucidates a clear construction on social license. And if you don't tell anyone in advance of asking the question whether they're supportive of nuclear or not, you get an ambiguous response, 50-50. But if you start engaging and say, look, nuclear is the backbone of clean energy provision today. Advanced nuclear can deliver a hydrogen economy by combining with certain technologies such as carbon engineering. Those polling results go from ambiguous to positions where people are clearly in support of existing nuclear and also nuclear innovation. So the PR point is basically a very good one. We are fortunate that there are many organisations that are taking that positive message, that good news message, out to the general public, and that includes politicians and governments. We in the nuclear sector cannot make progress without a public partnership. You can't deploy nuclear unless you have the support the governments in the markets you're seeking to deploy your system first. In our case, it's we're seeking to deploy first systems in Canada, shortly thereafter the United States, and potentially the UK as well. The UK has a growing, quickly escalating energy need that can only really be fulfilled by nuclear. And from our perspective, we are seeing that those governments are becoming increasingly supportive of nuclear, and that support is not, simply sound bites at a podium. That support is expressed in clear policy positions, and those policy positions and that enacted policy is backed by public funds. So to your point, there's a growing constituency here that is taking that good news nuclear story out to the general public, and if when they're told that good news nuclear story, as you see from polling data already, they become more supportive of nuclear.
And I'd like to add to that, you've struck on one of the biggest challenges that nuclear has had for decades. And I think for a long time, the nuclear industry sat back and said, oh, they'll get it, they'll come. It's good technology, but we can't do that anymore. And we look at the Clean Energy Ministerial. Those of us here probably all know that nuclear is the backbone of clean energy. But until the 9th Clean Energy Ministerial last year, there was nothing associated with nuclear. And that's an issue. We've gotten over some of that challenge now in that you hear it being talked about in all these sessions, and that's a fantastic step forward. And what we really need to do is inform at multiple levels, that general public level, get good information out, those making policies, the government decision makers, and there's a lot more organizations willing to help us, folks like Generation Atomic and other groups out there that maybe aren't trained nuclear engineers, but they believe in the technology because they've taken time to learn about it, and they can be assets in helping us reach the general public that maybe don't trust the scientist or engineer that's being paid by that industry. And I think we can take advantage of our partners that we have in the renewable energy sector that have begun to understand what it is that we're offering in this technology and putting them out there to talk to the general public, to talk to the decision makers, to help carry our message forward. And without that, we won't be successful. But we're making really good progress. I think we're on the right track.
Great.
I realize I'm the moderator, but this is much of what my research and scholarship is based on. So if I may also throw in my own piece of this. The support for nuclear tends to be very lukewarm. There isn't the same sort of committed support. When somebody is committed to supporting nuclear, and generally speaking, it's the people who have deep technical knowledge of nuclear who wind up being committed to supporting nuclear, when something like Fukushima happens, the people with a deep emotional identity based on, I am somebody who likes nuclear, I appreciate nuclear. When something like Fukushima happens, there's a desire to go in and dig through the sensationalism down to the facts. I don't believe that we as a society are taking climate change seriously. And I am speaking as somebody who is one of the reviewers for the Intergovernmental Panel on Climate Change. And when I read through that document, I was really, really distraught to discover not only was nuclear not really being seriously considered, hydro wasn't being seriously considered either. So it's not just nuclear that's been set by the wayside, but we have focused so much on renewable energy that we've missed the point, which is one of the things I'm really excited about with your company. The point is not renewable. We have plenty of energy. We have all the energy we need. There is no lack of energy. There's a huge abundance of energy. What we need is a system that will actually allow us to deploy that energy with no carbon emissions, or if possible, a reduction of carbon in the atmosphere. So what do we need to do? We need to listen better, and we need to actually start, no, I think we just need to listen better. And it's great we can come up with these technologies, but until people are enthusiastically pursuing nuclear the way they enthusiastically pursue wind and solar, which need to be included as well, and geothermal and tidal and hydro, once we start enthusiastically saying, take the renewable energy off and put on what do we do to reduce carbon emissions, that's when the game change happens. But you're right. We definitely need to stop sitting back and waiting for them to come to the technology. You're absolutely right about that.
I'll take a sort of slightly contrarian view on that position. I mean,
Please do.
Nuclear's problem in terms of the current deployment and future deployment is based on cost. It's not really based on social license. The UK, it would be building many new systems to replace its existing fleet if the cost of those systems was more cost competitive than building a new plant with conventional technologies today. The US fleet would be probably expanding if conventional reactor plants, new conventional reactor plants, could be built on time, on budget, with lower risk, and more critically, could be funded with private capital. The problem with conventional nuclear today is that it has lost its relationship with private capital. It is commercially redundant in competitive global energy markets. So the opportunity, the great opportunity for nuclear innovation today is to establish that relationship with private capital, because the commercially productive innovation in any space creates a better product. The way we operate our societies is to have free market enterprise and have competitive markets. And if we have competitive markets, we also have to diagnose the problem with nuclear. The problem with nuclear is simple. Conventional reactor systems are too expensive. So what we're seeking to do at Terrestrial Energy is to focus on that market problem, and we're innovating to solve it. We're innovating it with a reactor design that doesn't use water in a highly pressurized cooling system, which has probably driven that technology choice has probably substantially contributed to the cost inflation of conventional reactor power plants today. We avoid that cost inflation spiral that the existing industry has been subjected to for the last 20 years. We use a thermally stable molten salt in an innovative design, and in doing so, we believe we solve the market problem. In solving the market problem, the way capital works, capital will flow with great interest and enthusiasm to support deployment, and we've seen this with wind and solar. Wind and solar initially were supported with aggressive public policy. That aggressive public policy established these technologies, and these technologies are now these energy technologies. The deployment of them is being driven increasingly by private capital. It remains to be seen what happens when those policies are totally withdrawn. But certainly there's substantial private capital interest in wind and solar. So the opportunity for nuclear today is to engage with private capital. I don't really accept the social license issue.
We will have to debate this over a beer at some point,
yes.
because I have many things to say, but I want to give each of our panelists a chance to have one closing thought.
Okay, I'll make it real simple. Because I'm a simple guy, not a nuclear person. So here's what I would want each of you. Sorry, I didn't mean that in a negative way. Here's what I want each of you to take away. Think of the atmosphere as a bathtub. It's a very simple analogy, but it's a very powerful analogy. It's full of water, and there's too much water in it, and we have the tap on full. We're emitting continuously. So what happens? It overflows. So we have so many people focused on turning down the tap, but you can't turn it down. It's not going to zero. It's going to keep, best case, it's going to keep dripping. And what will happen in your home if your bathtub is full and it's dripping, it's going to overflow and wreck the house. Have you ever seen a bathtub anywhere in the world without a plug? Right? How do you solve this problem? You have a plug, and you pull the plug and you drain the water out of the bathtub, the CO2 out of the atmosphere. And if the tap is still running to the degree that you can't turn it off, if you've got a plug, the bathtub doesn't overflow. And that's what carbon engineering's technology does. We're the plug in the bathtub. Very simple way of looking at it. And remarkably few people, frankly, in the climate change world, understand the criticality of turning down the tap and pulling out the plug.
I like that analogy. I'm going to have to borrow that one.
Very good.
Just in closing, I do want to respond to something that Simon said with regard to cost. Absolutely. We can have the most brilliant technologies. If we are not competitive on cost, it doesn't matter. And that's a horrendous idea. In the US, you're absolutely right. We're having a hard time building a new plant on schedule, on budget. We've blown those curves. But it's happening in other places. In Asia, they're building plants on schedule, on budget, at much lower cost. We need to learn from that. We need to remember in the US and elsewhere how to do these large projects effectively and to do them within a budget that has been set. But we also need to look at innovation and adopting new technologies that can reduce costs in different ways, such as what you were describing, small modular reactors that are bite-sized pieces, a lower cost of capital to invest in that project. We also need to look at how these things are valued within the markets. The market is absolutely a part of this, but right now, in the US at least, I pay for the cost of an electron. All the other things that are brought to the table by baseload energy sources, by nuclear sources, and by fossil sources as well, they're given for free. We look at the inertia that's offered to the grid by these large-scale systems. That's for free to the grid. And once that's not there, we've got to replace it with something. So there's a lot of discussions going on about levelized cost of energy, not just electricity. What do we need to be valuing, or what do we value that we're just not paying for and don't realize that we're going to miss it when it's gone? And so there's a lot of factors here: innovation, keeping projects moving forward, as well as market reform and understanding what needs to be done there. So thank you.
Yes, I'll just finish off on the issue about sort of a good news story. The problems we face with energy, they are in part climate and in part energy poverty as well. It's in part a climate problem, but if you look at the energy poverty problem, that's about 5 times the size. You can, when you think about that problem on a day-to-day, you get rather despondent. There are no transformative energy technologies that are available to actually solve this problem in the time frame we have for the better world that we aspire to leave our future generations. So I certainly think that with respect to the technologies that the technology that carbon engineering is looking to put together, and also our technology as well, market competitive nuclear that is a clean energy alternative to fossil fuels, you have those transformative, revolutionary technologies that I think give great hope to the future clean energy economy that we all aspire to have.
And I'm going to push back with a contrarian view on that, which is, in the last 25 years, we have cut energy poverty in half. We have seen tremendous progress on every part of the Human Development Index. And the way we have done that is by introducing energy into places that people didn't have access to energy before. So I think the good news story is better than you are saying. And I think that your company and your lab will all be providing very important pieces for that very good news story going forward. Let's thank our speakers.